Okay, everyone, welcome back. It's 8 p.m. again for today, and let's continue reading the book Pattern Recognition Machine Learning together with me. Okay, we are gonna start from probability theory. Okay, today, which is 1.2, section 1.2. Okay, let's dive into it. A key concept in the field of pattern recognition is that of uncertainty. It arises both through the noise on measurements as well as through the finite sets of data sets. Okay, probability theory provides a consistent framework for the quantification and manipulation of uncertainty. Quantification. First of all, you have to kind of quantitatively being able to quantitatively measure it. Second of all, being able to manipulate it. Okay, and forms one of the central foundations for pattern recognition. When combined with decision theory, discussed in section 1.5, it allows us to make optimal predictions, given all the information available to us, even though that information may be incomplete or ambiguous. Okay. We'll introduce the basic concepts of probability theory by considering a simple example. Imagine we have two boxes, one red and one blue. Okay. In the right box, we have 2 apples and 6 oranges. One blue and one red. In the blue box, we have 3 apples okay, and 1 orange. This is illustrated in figure 1.9. Now suppose we randomly pick one of the boxes, and from the box, we randomly select an atom fruit, okay? And having observed which sort of fruit it is, we replace in the box from which it came. We could imagine repeating this process many times. Let us suppose that in doing so, we pick the right box 40% of the time, and we pick the blue box 60% of the time. Okay? And that when we remove an atom of fruit from a box, we are equally likely to select any of the pieces of fruit in the box. So first of all, you have to select the box, okay? And second of all, you have to pick a fruit outside of the box. In this example, the identity of the box that will be chosen is a random variable, which we shall denote by B, capital B, okay? So this letter, this notation represents which box you're gonna choose. This random variable can take one of 2 possible values, namely R or B, which is the red box or the blue box. Similarly, the identity of the fruit is also a random variable and will be denoted by F. It can take either of the values, A for apple or O for orange. Okay. To begin with, we shall define the probability of an event to be the fraction of times that event occurs out of the total number of trials. In the limit that the total number of trial goes to infinity, okay, the probability of selecting the right box is 4 over 10, and the probability of selecting the blue box is 6 over 10. We write these probabilities as this notation and this notation. Note that by definition, probabilities must lie in the interval 0 to 1 closed interval, okay? Also, if the events are mutually exclusive and if they include all possible outcomes, for instance, in this example, the box must be either red or blue, then we see that the probabilities for those events must sum to 1, okay? We can now ask questions such as, what is the overall probability that the selection procedure will pick an apple? Okay. So remember that in the right box, there are two apples and 6 oranges, and in the blue box there is 1 apple and but there is 3 apples and 1 orange. Okay. We can answer questions such as this, and indeed much more complex questions associated with problems in pattern recognition, once we have equipped ourselves with the 2 elementary rules of probability, known as the sum rule and the product rule. Having obtained these rules, we shall then return to our boxes of crude example. Okay. So in order to derive the rules of probability, consider the slightly more general example shown in figure 1.10 involving 2 random variables, x and y. Okay. Which could, for instance, be the box and fruit variables considered above. We shall suppose that x can take any of the values xi, where I equals to 1 to capital M, and y can take the values yj, where j is from 1 to L. Consider a total number of n trials in which we sample both of the variables x and y, and let the number of such trials in which x equals to small xi and y equals to small yj be nij. Okay, so basically, if you select I for the random variable x, okay, and if you select j for the random variable y, then basically the combination of them, which is ij, which is basically the final outcome or combination that you selected. Also, let the number of trials in which x takes the value of xi, which is irrespective of the value that y takes, be denoted by ci, and similarly, let the number of trials in which y takes the value yj be denoted by rj. Okay. The probability that x will take the value xi and y will take the value yj is written as x equals to xi, y equals to yj. It's called the joint probability of x equals to xi and y equals to yj. It is given by the total number of points falling in the cell ij as a fraction of the total number of points. Okay, so what is n here? N is basically all of the possibilities, right? Okay. So okay, so n is actually the number of trials you took. Okay, so how many experiments you repeatedly did, and that is going to be n. And small nij is basically the number of times that it falls into the combination of I and j. Xi equals to xi and y equals to yj. Okay, and the probability of the occurrence of this joint probability is basically the number of times that I and j occurs together, normalized by the total number of trials. Okay, so here we implicitly considering the limit that capital N goes to infinity. Similarly, the probability that x takes the value xi, irrespective of the value y, is written as this. Okay, so you can consider this as a marginal probability. Okay, so this is without the occurrence y equals to yj. Okay, it's given by the fraction of the total number of points that fall in column I. Okay, so basically, if you denote the number of times that a single trial falls into the column I, then basically the occurrence of x equals to xi is going to be ci divided by capital N. Okay, because the number of instances in column I in figure 1.10 is just the sum of the number of instances in each cell of that column. We have, okay, ci is equal to, basically you integrate over all the possible j of that column. Okay, so j is basically from 1 to how many are there? 1 to L, not capital G, 1 to L. Okay, and nij. And therefore, from 1.5 or 1.6, we have this. Okay, so basically we are integrating over j equals to 1 to L. Okay, which is the sum rule of probability. Note that P, the probability of x equals to xi, is sometimes called the marginal probability. Okay, because it is obtained by marginalizing or summing out the other variables. And in this case, it's basically summing over all possibilities y. If we consider only those instances for which capital X is equal to xi, small xi, then the fraction of such instances for which y equals to yj is written as the conditional probability or conditional density. Okay, so given the case that x equals to xi, what is the probability is y equal to yi? Okay, so this is a conditional probability, and it is obtained. Okay, so the numerator here is still the combination that of ij occurring together, and the normalizer here is a little bit different because it's conditional upon the case that x is equal to xi. Then we know the number of occurrences that the trial falls into column I is basically ci, so we normalize it by ci rather than by total number of trials. Okay, we can then derive the following relationship that basically, if you derive it, nij divided by n, okay, is actually equal to nij divided by ci divided by n. And this part, if you look at it, it's actually the conditional probability of y equals to yj, conditional x equals to xi. And okay, this is this part, and this part is basically that x equals to xi. Okay, yeah. So if you multiply these two parts together, then it's going to be y equals to yj, conditional x equals to xi, multiplied by x equals to xi, which is equal to the joint probability of y equals to yi, comma x equals to xi. Okay. which is a product rule of probability. So far, we have been quite careful to make a distinction between a random variable, such as the box capital B in the fruit example, and the values that a random variable can take. For example, R, small r, if the box were the right one. Thus, the probability that B takes the value R is denoted by, okay, so the first part here is actually the random variable, and the second part is actually the value that the random variable takes. Okay, although this helps to avoid ambiguity, it leads to rather cumbersome notation. In many cases, there will be no need for such. Instead, we may simply write probability B to denote the distribution or the random variable B, or probability of R, okay, to denote the distribution evaluated for the particular value R, provided that the interpretation is clear from the context. Okay, so there's no universal kind of written style, but you have to make sure that whatever style you adopt, you have to make it clear that people can understand. Okay, with this more compact notation, we can write the two fundamental rules of probability theory in the following form, which is, first of all, the sum rule. Okay, if you integrate from a joint probability, if you integrate over one of the variables, and what you will get is actually the marginal probability of the other random variable. Okay, the product rule is basically that the joint probability is equal to the conditional probability times the marginal probability. Okay, multiplied by the marginal probability. Okay, so we are going to skip this part, which is pretty basic, fundamental, and straightforward to understand, actually. So from the product rule, together with the symmetry property, which is joint probability of x, y is equal to joint probability between y and x, okay? If you interchange the order of the two terms, that doesn't really matter. Okay, we immediately obtain the following relationship between conditional probabilities, which is called the Bayes theorem. Okay, and which plays a central role in pattern recognition and machine learning. Okay, so this formula is really, really, really important. Okay, a lot of machine learning algorithms are developed on top of this principle here, which is called Bayes theorem. Okay, and there is a category of inference which is called Bayesian inference. Okay. Using the sum rule, the denominator, okay, the denominator in Bayes' rule can be expressed in terms of quantities appearing in the numerator. Okay, so the denominator in the Bayes' rule can be expressed in terms of the quantities appearing in this numerator. Okay, so what is Px? So Px, as we have discussed before, is actually basically you integrate one of the variables in the marginal, in the joint density, right? And the joint density can further be written as the conditional density multiplied by the marginal density. Okay. And this form is typically, the Px here is for most of the time, which is intractable. And we have to kind of approximate this posterior, you will see in a lot of machine learning algorithms, okay? And we often treat this part as a constant. Okay. So suppose that y is some parameter that you want to infer, right? And x is some data that you see, which is used as evidence, right? And Px, the probability of x, is generally distribution in x. We assume that it's a kind of a constant. So we normally omit this part and basically say that y given x is kind of proportional, okay, to the evidence term multiplied by prayer. So prayer is something that we already had, okay, about the term that we want to infer, and we want to combine it with the evidence term to get a kind of approximate inference for the posterior term. Okay, for the parameter that we want to infer. Okay, so we can view the denominator in Bayes' theorem as being the normalization constant required to ensure that the sum of the conditional probability on the left-hand side over all values of y equals to 1. Okay. In figure 1.11, which is where is 1.11? Okay, this is 1.11. So we show a simple example involving a joint distribution over two variables to illustrate the concept of marginal and conditional distributions. Let's actually look at it. Okay. An illustration of a distribution over two variables, x, which take 9 possible values, and y, which takes 2 possible values. Okay. The top left figure shows a sample of 60 points drawn from a joint probability distribution over these variables. The remaining figures show histogram estimates of the marginal distributions, px and py, as well as the conditional distribution corresponding to the bottom row in the top left figure. Okay. Okay, so if you only look at py, right, and y has 2 values, right? So it's kind of a distribution over the 2 values, right? You can see that y equals 2, the amount of points is a little bit fewer than the number of points that fall into the value of y equals to 1. So the bar is actually shorter here compared to y equals 1. And if we just look at x, right, we can see that basically for each corresponding value of x, it corresponds to a bar associated with it. Okay, so we can see that the middle ones, they're pretty large, they're pretty high, okay, they're pretty tall. So we can see actually here is actually the case. So there are a lot of points in the middle values of x. Okay. And if you just look at, take a conditional density, only looks at y equals 1 and the corresponding distribution on x in terms of the conditional density looks like this. So you see that the majority of the points fall on the left-hand side part of x values, which is also the case here, right? Okay. So again, we know that these probabilities are normalized so that if we take a conditional density, okay, the posterior probability for all values, not the posterior, but the conditional density integrated over all the values of the fruit is going to be equal to 1. Similarly, right? If you take the conditional probability conditioned on the other value of the random variable b, the probability of all the values over f is also going to sum to 1. Okay. We can now use the sum and product rules of probability to evaluate the overall probability of choosing an apple. Okay. from which it follows using the sum rules, we can get this, which is straightforward, right? Suppose, okay, so yeah, let's finish this part and let's finish this part and then we take a break, okay? So suppose instead we are told that a piece of fruit has been selected and it is an orange, we would like to know which box it came from. This requires we evaluate the probability distribution over boxes conditioned on the identity of fruit, whereas the probabilities in the previous subsections give the probability distribution over fruit conditioned on the identity of box, right? So we can solve the problem reversing the conditional probability using Bayes' theorem, right? So let's review what Bayes' theorem says, right? So PB, the probability of box over fruit, is going to be equal to, you reverse this, right, which is called the evidence term, and multiplied by the prior term, right, integrated over a constant. We can solve the problem of reversing the conditional probability by using the Bayes' theorem to give this, right? From the sum rule, it then follows that probability of capital B equals to small b, condition on capital F equals to O is 1/3. Okay. We can provide an important interpretation of Bayes' theorem as follows. If we had been asked which box had been chosen before being told the identity of selected atom fruit, then the most complete information we have available is provided by the probability P capital B. We call this prior because it is the probability available before we observe the identity of the fruit. Okay. So you can consider something when you try to infer the parameters of a model, right? You already have some prior belief. For example, you assume that it's Gaussian distribution, but you want to kind of use some actual data to confirm your assumption or like update your assumption. And that is going to be called an evidence term, right? So once we are told that the fruit is an orange, we can use Bayes' theorem to compute the probability, okay, which we shall call the posterior probability, okay? So you have some prior belief about what the distribution of the random variable B that you want to infer. And after getting some data, right, you update your belief about what the distribution of random variable B should look like, conditioned upon the data you observe. Because it is a probability obtained after we have observed capital F. Note that in this example, the prior probability of selecting the right box was 4/10, so that we were more likely to select the blue box than the right one. However, once we have observed that the piece of selected fruit is an orange, okay, we find that the posterior probability of the right box is now 2/3. So that it is more likely that the box we selected was in fact the right one. The result accords with our intuition, as the proportion of orange is much higher in the right box than it is in the blue box. And so the observation that fruit was an orange provides significant evidence favoring the right box. Okay. In fact, the evidence is sufficiently strong that it outweighs the prior and makes it more likely that red box was chosen rather than blue one. Finally, we know that if the joint distribution of two variables factorizes into the product of the marginals, something like this, then yx and y are saying to be independent. Okay. So in this case, if you manipulate this formula, let me show you something interesting. So xy, so this suggesting independence of xy, right? If you move this part, for example, to the left, let's actually move this part for the convenience, okay? Equal to px, and this is going to give us x conditional y, px, okay? So if this happens, so the conditional density of x given y is equal to the condition is equal to the marginal density of x, then basically y didn't play any role here, right? So basically means that x is independent y, right? For instance, in our boxes fruit example, if each box combines the same fraction of apples and oranges, so the probability of selecting say an apple is independent which box is chosen. Okay, so that's the first part of the probability theory of 1.2. Okay, so next we are going to see, so I think the authors give up very good examples to illustrate what is conditional density. Okay, what is marginal density? Okay. Actually, I should be careful of using the term density because it generally refers to a continuous kind of input space. But the basic idea is that because the case here is actually discrete. You have a discrete input space rather than a continuous input space. Okay, so it's gonna be something called probability mass function. Okay, so I should correct myself that it's not density. And actually, in the next subsection, we are going to see the term probability densities. Okay, so if you want to follow strict terminology, then this is something that is referred to as probability mass function. Okay, where the input space, okay, is actually discrete. Okay, so probability is something that basically you take an input space and map it to a bunch of values that sum up to 1. Okay, a bunch of non-negative values that sum up to 1. Okay, so let's take a short break and come back. Okay, in a few minutes. Okay, let's continue. Let's look at probability densities, okay? So the example we looked at just now is a number of discrete possibilities, right? For example, there are just two boxes, right? And those are just discrete numbers. What if you have a continuous kind of input space? So in that case, we'll use probability densities to describe it, okay? So as well as considering probabilities defined over discrete sets of E1s, we also wish to consider probabilities with respect to continuous variables. We shall limit ourselves to a relatively informal discussion. If the probability of a real valued variable x falling in the interval is given by px times delta x, for delta x goes to 0, okay, then px is called the probability density over x. This is illustrated in figure 1.12. Okay. The probability that x will lie in an interval AB is then given by px integrate over the interval from A to B. Okay. Whether it's closed or it's open, it doesn't really matter because it's continuous. The input space is continuous. Again, let's reread this definition. So if the probability of a real valued variable x falling in the interval x to x plus delta x is given by px delta x. So px is actually the hat, right? And delta x is actually the width of the interval. So width times hat, width multiplied by hat. Okay. Then px is called probability density over x. Okay, so if the idea is that if you take a very fine grained interval, very, very small interval, this interval is as small as something very close to 0. And in this case, okay, the probability of this random variable fall in this interval is defined by the area, okay, the width times hat. Then then basically px is called the probability density over x. Okay, if you take a very, very small interval that is close to 0, and the probability that the random variable x fall in this interval is actually the width of the interval multiplied by px. The px is called the probability density over x. Okay, so that's the definition here. Okay. So let's look at figure 1.12 to get a better understanding of this. So the concept of probability for discrete variables can be extended to that of a probability density over a continuous variable x. And it's such that the probability of x lying in the interval x to x plus delta x is given by px multiplied by delta x for delta x that is super close to 0. Okay, the probability density can be expressed as the derivative of the cumulative distribution function, capital Px. Okay. So if you look at this capital Px, the cumulative distribution function is basically how much total density we already have up to this point, right? So if you look at this area, right, this area, the density is a little bit high. So the slope of this CDF, we call it CDF, which is short term for cumulative density function, right, is increasing a little bit faster than this part, right? And if you look at this part, the density is a little bit lower than this part, so the increasing speed of the CDF, the cumulative distribution function, is going a little bit slower, right? The slope is becoming smaller. And if you look at the later parts, right, the density is super high, right? For example, this area, then basically the slope of the CDF is going to be quite high, right? So yeah, because probabilities are non-negative and because the value of x must lie somewhere on the real axis, the probability density Px must satisfy the two conditions. So first of all, at any certain point, okay, at any certain point, the probability density should be greater than or equal to 0. So if we don't have any constraint, then it's basically negative infinity to positive infinity. Okay, and the integration is going to be equal to 1, the integration over all the possible values of x. So under a nonlinear change of variable, a probability density transforms differently from a simple function due to the Jacobian factor. Okay, for instance, if we consider a change of variables, x equals to gy, the function fx becomes fy tilde equals to fgy, right? Now consider a probability density over x that corresponds to a density over y with respect to the new variable y, where the surfaces denote the fact that probability density of x, probability density y are different densities. Observations falling in the range x to x plus delta x will, for small values of delta x, be transformed into the range y plus y to y plus delta y, where the probability density of x, delta x, is approximately equal to probability y times delta y. Okay. One consequence of this property is that concept of maximum of a probability density is dependent on the choice variable. Okay. And that this integration satisfies this as shown in figure 1.12. Okay, so you basically the slope of the CDF cumulative distribution is equal to the density. Okay, if the density is high, then the slope of the CDF is high. If the density is low, then the slope of CDF is low. Okay. By CDF, again, I referring to the cumulative distribution function, okay? If we have several continuous variables, x1 to xd, denoted collectively by the vector x, okay, then we can define a joint probability density, which is that P of vector x is equal to the joint probability of all of its elements in the vector, okay, such that the probability of x falling at infinitesimal volume delta x containing the point x is given by px delta x. This multivariate probability density must satisfy these two equations. Again, at any given point, the probability value, density value should be non-negative. Okay, non-negativity. And the second is that integration is 1. Okay, in which the integral is taken over the whole of X space. We can also consider drawing probability distributions or a combination of discrete and continuous variables. Okay. Note that if X is a discrete variable, then Px is sometimes called a probability mass function, as we talked about. So the example we looked at in the previous subsection, which is the boxes, choosing between boxes, choosing between fruits in the boxes, is actually a discrete example. So there are limited number of choices there, right? So this term probability mass function, because it can be regarded as a set of probability masses concentrated at a lot values of X. Okay. The sum and product rules of probability as well as Bayes' theorem apply equally to the case of probability densities or to combinations of discrete and continuous variables. For example, if X and Y are two real variables, okay, then the sum and product rules take the form of this. So integrate over the other variable, which is Y here, then you get a marginal probability density of X, okay? And the joint probability density is the multiplication or the product between the conditional density of Y given X and the marginal density of X, okay? A formal justification of the sum and product rules for the continuous variables requires a branch of mathematics called measure theory, okay? Unless outside the scope of this book, its validity can be seen informally, however, dividing its real value into intervals with, I don't know how to call it here, but with the triangle notation here, okay? And considering the discrete probability distribution over the intervals, take the limit that this triangle is approaching 0 and turn sums into integrals and gives the desired result. So the next subsection is about expectations and covariances, which is critically important, I have to say, okay? Because, yeah, it's a really useful concepts, okay? Not only for statistics, but also for machine learning. So let's look at it, okay? So after that, it's going to be pretty much the Gaussian distribution, the Bayesian probabilities, okay? Not super much left. Okay, so expectation covariances. one of the most important operations involving probabilities is that of finding weighted averages of functions. The average value of some function fx under a probability distribution px is called the expectation of x, expectation of fx. Okay, it will be denoted by expectation of f. Write it down here. Okay, and this expectation is basically taking a weighted average of all the possible values of fx. Okay, or and the according weight is basically the according probability that x appears with that appears with that value. Okay, so that the average is weighted by the relative probabilities of the different values of x. Okay, in the case of continuous variables, expectations are expressed in terms of integration with respect to the corresponding probability density. This thing. Okay. So in the case of the discrete probability, then it's going to be the sum over all of x. And in the case of a continuous density, it's going to be an integration over the valid range, interval range. Okay. In either case, if we are given a finite number of points drawn from the probability distribution or probability density, then the expectation can be approximated as a finite sum over these points. So you can call it a sample mean. Okay. We shall make extensive use of this result when we discuss sampling methods in chapter 11. Its approximation becomes exact in the limit n goes to infinity. Okay. Sometimes we will be considering expectations of functions of several variables. Okay. In which case we can use a subscript to indicate which variable is being averaged over. So for instance, okay, so if it's a joint if it's a joint probability density between x and y, then we just want to, you know, average over x, then we denote it using a subscript. Okay. So denotes the average of function with respect to the distribution at x. Note that this function will be a function, this term will be a function of y. Okay. We can also consider a conditional expectation with respect to a conditional distribution. Basically that yeah, basically that given the value y, what is kind of average of fx. Okay. Taking the average with respect to x. Okay. So this notation here is a little bit strange, but you can just try to get what it means. Okay. So the subscript here denotes that which random variable that we are taking the mean with respect to, right? And the weight is actually a conditional distribution of x given y, and the value is actually fx. Okay, with that analogous definition for continuous variable, the variance of fx is defined by this. Okay, so it's going to be expectation of the square of fx minus expectation of fx. Okay, so the square of the difference between fx and expectation of fx. Okay, so we can actually further expand this term here. How do we do it? So it's going to be expectation of fx squared minus 2 fx expectation of fx plus square of fx, right? Curly braces here, and it's going to be fx squared minus, okay? So here, let's, kind of pay a little bit attention here. So this part, if you take the expectation, it's going to be expectation of fx, right? And this part is already a constant, so it's a square, and the plus square of expectation of fx, then it's going to be expectation of fx squared minus square of expectation of fx, which is exactly what it shows here, okay? In particular, we can consider the variance of variable x itself, which is given by what? Given by this, right? Variance of x, if we take out the mapping, right? For two random variables, x and y, the covariance is defined by this thing, okay? So x and y minus expectation of x multiplied by expectation y, okay? Which expresses the extent to which x and y vary together. If x and y are independent, then the covariance kind of vanishes, okay? In the case of in the case of why is the case the covariance vanishes? So if we take a look at this, so what it says, xy, right? Xy, which is equal to integration sum over all the values of x and y, and joint density between x and y, right? And xy, right? So what is this term? If it's independent, it's fx, px, py, okay? And yeah, basically. So if you rearrange this, right? So x, y, right? Px, py, xy, right? Is going to be let's take these two parts on the further left, which is the x, okay, px, x, and then y, py, right? What is this? This is expectation y, right? And this is a constant with respect to x. So these two parts are independent, and this is the expectation of x. So this is exactly equal to expectation of x times expectation y. And in this case, expectation of x multiplied by expectation y minus itself is equal to 0 if x, y independent, right? In the case of two vectors of random variables x and y, the covariance is actually a matrix, okay? So if x is n-dimensional, y is n-dimensional, the covariance of x, y is going to be n by a matrix, okay? So why is that the case? Because x is n by 1, and y transpose is y by n, and this expectation term is going to be n by n. Same thing here, this expectation n by 1, and this expectation 1 by n, and this gives us 1 by n, okay? If we consider covariance of the components of a vector x with each other, then we use a slightly simpler notation, which is that covariance of x, okay, is defined by, okay, so 3 dashes here, 3 dashes here, right? Which is basically saying that this is a definition. So the covariance of x is actually covariance between x and x. Okay. So let's see how much we have for Bayesian probabilities. Yeah, so I'm going to stop here because we pretty much finished with the probability theory part of it. So we introduced the basic concept of probability mass function, probability density function, the conditional probability, the marginal probability, right? And also give an example to illustrate this. So let's pause here, and we are going to continue tomorrow. Okay, at I would say that possibly 8 p.m. So yeah, so let's see. If it's not 8, then probably 9, but let's see. So we're gonna continue tomorrow, and thanks for watching.